Hello, Karthik here. I am going to bring again a second video lecture. See, I'm starting from sitting room. The thing is, in my childhood, my mother used to tell me, study, study, study. And from morning to evening, I used to study. And my mother used to appreciate me now. Karthik is studying very nicely and he is doing hard work. But whatever mother said is wrong in terms of physics. Astonished, the laughing. That's why in physics, if something moves, then only you can say that work is done. If I do this, I'm just pushing this wall, I get tired because you would think that I'm doing some work, but there is no displacement of the board, there is no work done. It's said to be done whenever there is an external force acting on the body which displaces that body. Then only you can say that there is a work done in physics. Work done defined in this way. Remember, work done is a scalar quantity that can be obtained by taking the dot product of two vectors. Since force is a vector and displacement is a vector, I take the dot product of these two, I will get again a scalar. And this work done is a scalar quantity, can be greater than 0, can be lesser than 0, can be equal to 0. It can have positive work, here it is, you can have negative work, and also you can have 0 work. Now when can you say that you are doing a positive work? See, all depends on this line, F and X, in what way you are applying force, in what direction you are applying force. Suppose, if I have a mass over here, simply maybe the BMW car, no problem. What I'm going to do is I'm going to pull it from this way. So I'm going to pull this way. So this is the direction of external force applied. And because of pulling, and this mass will be displaced to another point, maybe this one. This is point A, this is point B, and there is a displacement X. Now, what I'm going to do is, I'm going to take this angle as theta, and I'm going to resolve this F into two components. One is horizontal component, F cos theta, and another one is vertical component, F sin theta. Remember, this vertical component is exactly normal to the X or perpendicular to the displacement. So there is no contribution for work because of this F sin theta. Only one term contributes, that is this horizontal component, that is F cos theta. So that's why, remember, so this work term depends on in which direction you apply force, or the angle between the force and the displacement. So all that matters. Now this way, so I am going to write this as magnitude of F, magnitude of X cos theta, where theta is angle between this applied force, external force, and the displacement. Now I'm going to discuss different cases. So work done can be positive, greater than 0. When can you make this guy greater than 0? Very nice. F is a force, is of course a positive quantity. X, displacement, again a positive quantity. All matters is this cos theta. So you can make this guy as greater than 0 only when cos theta greater than 0. And the maximum work you can say only when theta is equal to 0. What does that mean? See, the angle between F and X should be 0. That means you are applying the force and the displacement are in the same direction. So that's why angle between displacement and force is equal to 0. That's why you can say that maximum work done, positive work done. An example? Sure. See, very simple example is a spring over here. It is at rest, no problem so far. What I'm going to do is I'm going to apply the force to the spring so that I'm going to make it expanded. So I'm going to expand the spring. So this is the mean position. So after external force, it could be extended maybe till here. So what I have done, I have applied some external force to extend it. Because of the extension, because of the external force, there is a displacement. So the force and the displacement are in the same direction, so that I can say that I have done a positive work. Another example. You are actually playing tug of war, and this is going to be very lucky day today, and you're going to win the match. And the work done by you, if you win the match, is going to be positive because work you do and in the force you apply and the displacement are in the same direction. So work done is equal to, is positive. That is greater than 0. This work done lesser than 0, you can have only when cos theta lesser than 0, and you can have very minimum work when theta is exactly equal to 180 degrees. Theta, angle between force and displacement. If the angle between this force and displacement 180 degrees this way, you are applying this way and displacement in this direction, then you can say that there is very minimum work because angle between F and X is 180 degrees. So third case is, so here I can give some examples. Of course I told you tug of war, and if your day is going to be very bad, you are going to lose the match. Even though you get tired, the work done is negative. That's fine. However, what about this guy? W is equal to 0. So when can you make that W is 0? 3 possibilities. One is F is equal to 0, that you don't apply any force. I'm very comfortable here, I'm just standing here. Maybe I can stand from morning to evening and the work done is equal to 0 because there is no displacement. So there is no force, of course. And this F is equal to 0. And next possibility is X is equal to 0. If there is no displacement, no work done. So another possibility is making cos theta is equal to 0. So when can you make this cos theta 0? Theta is 90 degrees, pi by 2. That means if you apply force perpendicular to the displacement, that is theta 90 degree, then that would not be any work. That's the third case. I got bag over here. What I'm going to do is, I'm going to lift this bag from bottom to top, and I'm going to keep it down. Lifting up, keeping it down. So this is what I'm going to do. Now I'm going to calculate what is the work done in lifting the bag. That work done is equal to the dot product of force and displacement, which implies magnitude of F, magnitude of X, cos theta, where theta is the angle between force and the displacement. So far so good. Now, when I lift back up, the work done by Karthik is the force applied by Karthik dot the displacement of the bag. And remember, there is actually I am taking a bag up and I am just actually lifting bag up, and the displacement also in the same direction. So force and displacement having angle 0, so that's why maximum work done, that is positive work, greater than 0, that is positive work. But remember, there is also a work done by gravitational force. So this is work done by Karthik. This is work done by gravitational force, which is the dot product of force and displacement. But the force is by gravity. But here, gravitational force always acts in downward direction. So this is going to be the displacement direction. This is going to be the gravitational force. And the angle between gravitational force and displacement is 180 degrees. So that's why cos 180 is minus 1. So minus F, which is lesser than 0. That means when I just bring this bag up, I'm just going to lift up, I'm doing positive work. And exactly at the same time, the gravitational force doing negative work. And I can do this. So I'm doing positive work, gravity does negative work. When I do the reverse one, I'm doing negative work, gravity does the positive work. So I can keep doing this from morning to evening. Positive work, negative work. Positive work, negative work. Positive work, negative work. I can keep doing this from morning to evening. Don't get confused with the word tiredness and the work. If you calculate the total work, it's equal to 0. Fx minus Fx add that, and the total work is equal to 0. So even though the total work is equal to 0, I would get tired. So you can get tired without doing any work. Very, very straight. No problem, this is physics. Little bit discussion on energy. So listen to me. You are doing some work. If you are more capable of doing work, then you can say that you are very energetic. So it depends on how much work you can do, in what way you can do work. So that's how energy is defined. It's capable of doing work. So remember, for energy you have so many different sources. One starting from mechanical energy, that's what I'm going to discuss. And this chemical energy, electric energy, magnetic energy. There are so many nuclear energy. There are so many different types of energy. So in this chapter, I'm going to discuss about mechanical energy. So what is this mechanical energy? Remember, again, so this is a combination of kinetic energy and potential energy. So I will be telling you this time about kinetic energy. So what is kinetic energy? If something is moving, you can make it move only when you apply the force. Then you can say that the body is having some energy, that is energy of motion, which is kinetic energy. So energy possessed by a body whenever there is a motion of body. That is called kinetic. I'm going to consider a body which is at rest having mass m, which is displaced to a certain position with a velocity v. So initial velocity is equal to 0. And the displacement of the body is x. So I'm going to write third kinematic equation for this, for the constant acceleration case. Final velocity square is equal to initial velocity square plus 2 acceleration dot displacement. This is third kinematic equation. And of course this u square is equal to 0 for this case because initially it is at rest. You make it to move and with the final velocity v. So v square is equal to 2. So remember, let me consider acceleration and the displacement are in same, acceleration and displacement are in same direction. So that's why dot product of a and x is equal to maximum value of acceleration, maximum value of displacement, cos 0 is 1. So I'm going to write for a is equal to v square by 2x. Now I know the definition for work, which is equal to force dot displacement, and force is mass into acceleration dot displacement. As I told, acceleration and displacement are the same direction, so I don't have any problem writing ax because cos 0 is maximum 1. So a is here, v square by 2x into x. So x cancel, so v square by 2. This is nothing but work done. So I did work by applying certain force to make this guy to move from rest to a certain velocity v. So whatever work I have done by the external force, which is exactly used to gain the energy of the motion, that's why you can say that which is equal to kinetic energy v square by 2, because whatever work I have done, which is exactly equal to kinetic energy v square by 2. Now, so can I write kinetic energy in terms of momentum? Why not? So I have got P is equal to mv and kinetic energy is equal to v square by 2. I multiply and divide by which implies. So square v square, that is v whole square by 2m. V is nothing but P square by 2m. So kinetic energy is directly proportional to the momentum. So it will be increased very directly proportional to the moment. So kinetic energy is measure of mass and velocity. If the body is moving with a greater velocity, it would be having greater kinetic energy. I told you work done is dot product of force and displacement. Another side, I told you something about kinetic energies, energy of motion. Now, can I relate these two? One side work I have, another side kinetic energy I have. So I'm going to discuss on work energy theorem. For that, what I'm going to do is I'm going to take a body of mass m initially with a velocity u, which is displaced because of external force with a certain point, with the displacement x with the final velocity. Very simple case as well. Now, for the time being, I'm going to discuss for constant force. So when can we say that this is a constant force? If you plot a graph, x versus f. So this is displacement, this is force, external force. For every displacement, and there will be constant force. There won't be any variation of force. This is what I'm going to discuss, constant force. Remember, I have got Newton's second law, F is equal to ma. Since F is constant, mass however remains constant unless it moves with the speed of the speed of light. Acceleration also remains constant. So F constant, A has to be constant. So this is a very special case, that is constant acceleration. So that means I have to make use of the kinematic equation. I will do that because that kinematic equation is meant for the constant acceleration. So V square is equal to V naught square, that is U square plus V square is equal to U square plus 2A dot x, dot product of acceleration and displacement. What I'm going to do is now, I'm going to bring this U square this side, minus U square 2A dot x. So I will do some magic over here. Just I'm going to multiply m by 2 on both sides. It doesn't affect me, it doesn't harm me at all. Because I'm showing any partiality. I'm going to multiply this m by 2 to the both sides. And m by 2, v square minus m by 2, u square m by 2, 2 times a dot x. So 2 to cancel. So this is again a kinetic energy. I told you half m v square, which is final kinetic energy, because v is a final velocity, minus kinetic energy initial is equal to 2 to cancel. So m a, I can take it inside because m is a scalar. So that is force times displacement. So which is equal to work. So I got the relation. There's a bridge between work done by the force and the kinetic energy. So what this work energy theorem says is, whatever work done by the external force, that work done is exactly equal to change in kinetic energy. That is for constant force. I discussed work energy theorem for constant force. What if the force varies with the displacement? This is how it goes. So force versus displacement. Earlier it was very straight line. Now I have got some variation. Now force doesn't remain constant, it varies with the displacement. Now for this case, what I'm going to do is, I'm going to take very small displacement. I'm going to consider very small displacement. Let me say it is of dx. For the very small displacement, I'm going to consider what is work done. So that for the very small displacement, work done is equal to dw. So that work done dw is equal to force times displacement. And I have to make my language very better. That's why this dot code. That is this dot product of force and displacement. Now, for the very simplicity, I'm going to consider force and displacement in the same direction. So that's why magnitude of F, magnitude of dx, cos 0 is maximum. So that they are in the same direction. Now, so I have found what is work done for the very small displacement dx. But my intention is to find out what is the total work done from initial position to the final position. So I have to measure what is a total work done. For that, I make use of integration concept. So total work done is equal to integration of very small work done corresponding to the small displacement from initial to final, which is equal to from initial to final. And this dw is dot product of force and displacement. And of course I have written as f dx. I have no problem. I can remove this arrow marks, which implies. So what I am going to do is, I have this f, which f is equal to ma. Now acceleration is not constant. Earlier it was constant because force was constant. So I cannot make use of v square is equal to v naught square plus 2e here because acceleration is not constant. So that's why I am going to write f as ma, that is dx multiplied by dx, integration m. A phase acceleration which varies with the time, and that is dv by dt, which is the rate of change of velocity times dx. Going to do some mathematics here. Velocity is equal to rate of change of displacement. I'm going to write this dx, that implies dx is equal to v dt. So I'm going to substitute here. Work done is equal to mass is constant I took outside, integration of, so dv by dt multiplied by dx. So I'm going to write dx in terms of v and dt, v dt. So dt disappear, and m integration v with respect to dv, and you can integrate from initial velocity, that is u, to the final velocity v. That's why I wanted to find what is the total work done from the initial position to the final position. So that's why work done is m times integration v dt. It is a very simple integral. Work done is equal to m v square by 2, and this is from u to v, which implies for v I have to substitute once as y, another time as u, m v square by 2 minus m u square by 2. Again, this is kinetic energy. So kinetic energy final minus kinetic energy initial, got again work. So no matter whether it's a constant force or a variable force, so total work done is always equal to the difference in kinetic energy. That is final kinetic energy you have to use, the final and initial kinetic energy. Take the difference, you will get what is the total work. By the way, is this true always? You have to measure initial kinetic energy. To measure initial kinetic energy, you have to measure what is the velocity, and you have to measure the final kinetic energy, final velocity, you have to measure it. If you take the difference, is it always equal to work done? Not always. The reason is the work done is exactly equal to difference in kinetic energy only when the force involved in doing work is conservative. Next time I'm going to catch this. Thanks for watching.